Welcome everyone. So this is our 24th live stream geometry. So today I chose problems from the China Western Math Olympiad. So I think in previous live streams I did the China Northern and the China Southeastern, I think it was. So now this is the China Western. So really big countries tend to have lots of Olympiads. Same with like Russia. And so I don't know if there's another China one, but maybe we'll end up getting through all of them. So I think it's harder than the other China contests. And so as usual, if you'd like to join these live streams, feel free to email me at mgreenb801@gmail.com. All right, so I'm gonna share my screen. Hold on just a second. All right. So here's the first problem. So we have a triangle ABC with AB greater than AC. So I guess something like this. O and H are the circumcenter and orthocenter. All right, so let me do it like this. So here's the circumcircle. O is the circumcenter. H is the orthocenter. All right, so let's draw the three altitudes. I wish there was an altitude function in GeoGebra, but I don't think there is. So D, E, and F, I'll let those be the feet of the altitudes, and H will be the orthocenter. Let's erase some of the excess. All right. The line passing through H parallel to AB intersects AC at M, and the similar line intersects AB at N. Okay, so hold on just a second. So I'm gonna cheat. GHIJKL. So it intersects AC at M. Whoops. AC at M and AB at N. And I'm going to delete these points that I just added just to get the letters right. All right, so ANHM is a parallelogram, and we can hide the excess. L is the reflection of H over MN. I think I accidentally did this. Whoops. Yeah, I accidentally drew EH instead of HM. Let's see if that's what someone said in the chat. Hold on just a sec. This is driving me crazy. Okay, HM. And line OL and AH. L is the reflection of H in MN. Okay, so I'm going to draw that reflection. So basically, ALH or ALNM is an isosceles trapezoid. I bet L lies on the circle. Let's see. Yeah, I think that's not hard to prove that this point L has to lie on the circle. Let's see who else joined. Hey to Bayou and Hakan, thanks for joining. So we're just on the first problem here. This is the China Western Math Olympiad. So we'll probably end up proving that L lies on the circle. OL and AH intersect at K. L is the AQ point in general. I feel really embarrassed. I don't even know what a Q point is. I know it's in like I3435. He wrote a book, and Q points are in it. So let's see. So OL intersects AH at K. we want to show that KLMN is cyclic. Well, we know ALMN is cyclic. So yeah, we just want to show K lies on that same circle. Okay, so let's see, let's first try to prove that L lies on the circle, which it feels true. So feels like it's some spiral similarity stuff. Basically L would be the center of a spiral similarity, or A would be the center of a spiral similarity, taking L and M to LBC in that case. It's just the second intersection point of AH and ABC. Oh, no, but this isn't the circle with diameter AH. Or let's see. Are you saying L is, oh, L lies on both circles. Ah, interesting. HMN is similar to ABC. Because let's see, HMN is congruent to ANM, and is ANM obviously similar to ABC? No, ANM isn't similar to ABC. So can we prove are you sure HMN is similar to ABC? Let me check. So angle HMN is 67.8, ACB is 61.4. So that's not true. HMN isn't necessarily similar to ABC. Sorry about that. It's all right. Yeah, so how do we prove ALMN is an isosceles trapezoid? It looks, well, because, oh, I mean, L has to lie on this circle because angle NHM is angle NLM is angle NAM. So yeah, it has to be ANML is an isosceles trapezoid, but how do we show? Let's see. So we want to look at, it's probably just an angle chase, right? So we know ANML is cyclic, right? It is an isosceles trapezoid. Does it obviously follow from there that L lies on the circle? I guess it's the same as saying, yeah, it does obviously follow because A and L are symmetric about the perpendicular bisector of MN. That's true by symmetry. So yeah, L lies on the circle. We have to show that K lies on the circle. So yeah, basically, is that obvious that K also lies on the circle? I think it might be. Does L lie on that? L does lie on the circle with diameter AH. I saw that. I don't. Yeah, I don't know the proof yet, but it does. Maybe that's you just do an angle chase on angle LAE, and you show it's equal to angle I think that might just be an easy angle chase. Isn't it obvious if L is the McKell point? I mean, I guess L is the McKell point of A and M and ABC. So NMBC. Oh, L is the McKell point of NMBC? Yeah, because you're right. So, and but you're saying that makes it obvious that L lies on the circle with diameter AH? How does it follow that L, like I see that L is the McKell point of BNMC. How does it follow that L lies on the circle with diameter AH? All right, let's see if we can prove it. But it's probably not that hard of an angle chase, I would guess. But I don't even know if we need that. So ultimately, we want to show K M ln is cyclic. So I'm not sure what coaxiality lemma Arabian math is referring to. There's the power ratio lemma, which sometimes is called the coaxiality lemma. Maybe he's referring to that. The power ratio lemma. Yeah, I kind of call it the power ratio lemma. I think someone else calls it that too. But basically, if you can show that the ratio of the powers of F with respect to those two circles are the same as the ratio of the power of E with respect to those two circles, then ALEF is cyclic. That's basically it. So the power of F with respect to the circle would be Fn times Fa. So we'd have Fn times Fa over Fb times Fa. And we'd have, so yeah, we'd want to show Fn over Fb is Em over Ec. Is that obvious? I'm not sure. Similarity. Oh, because triangles NHB and MHC are similar. I think that OM is OM tangent to the circle. I think it is. And then ON would also be. Yeah. So the picture makes it look like OH and M are collinear, but that's not true in general. But obviously, OH and N are not collinear, so yeah. All right, I think we have, so yeah, so I can prove that ALEF is cyclic, ALEF and H are cyclic. Yeah, how do we show that K lies on this circle? I have one idea on how to do it. So we want to show that the angle between OL and AD, that's angle AKL, is equal to angle AML. Just thinking how to do that. But yeah, OM and ON are tangent to the circle, which is kind of interesting. 1 sec, guys. I'll be right back. All right, thanks everyone for waiting. Okay, so we want to show K lies on this circle. And I see Ahmed Youssef has joined. Thanks, Ahmed. All right, so I think removing O and trying to prove that KL is a diameter is better. Yeah, I think that also makes sense. So basically we want to show, so ANHM, yeah, ANHM is a parallelogram. And because ANHM is a parallelogram, it's obvious that ALMN is an isosceles trapezoid. Also, we know LNKM is harmonic. Okay, so let K be AD intersect the circle is kind of what you're saying. Okay, so yeah, let's hide this line. I kind of like your ideas. We want to show basically OK and L are collinear. You're done then, because so you said L and KM is harmonic. How do we know that? Because we don't know yet that ON and OM are tangent, right? Projecting through A gives it. Okay. So L. Okay. So oh, you're saying project through A onto this circle. Yeah, what's the best? Do you want to project onto AFHE or the big circle? It probably doesn't matter, I'm guessing, but AFHE. Okay, so then we'd have LFHE, and is it obvious that that's harmonic? Oh, because the tangents, because of that lemma that says, yeah, so the tangents at E and F concur on BC. Is it clear that LH passes through the midpoint also? I guess that's well known. Yeah, it's well known that that HL. I've proven this on my channel before. Because this line is a diameter basically. That's well known. Okay, so that pretty much proves it. I wonder if we really needed harmonic quadrilaterals. Maybe we did, but I'm going to write up the solution. All right, so but yeah, we used the power ratio lemma to prove L lies on. I wonder if we really needed all this stuff. Is there an easier way to prove that L lies on the circle through A, F, H, and E? I feel like it's overkill, but that's a lot of concurrent point. Are you sure about that? MN and EF don't look like they concur on BC. No, MN and EF don't concur on BC. It's all right. But I mean, I don't think we need that L lies on that circle, because if we project through A, we get LBC and that point. We want to show that those are harmonic. And there has to be a way to do that. So Anmol, what is your way without using ALEFH? LMN is similar to LBC. And that finishes it. Okay, so once we know LMN is similar to LBC, and then, so yeah, that's true by spiral similarity. But then how do we show that LK is a diameter? So, okay, so that would mean LK is a diameter if an LMC equals LKH. And from there, I mean, yeah, that's true by the same spiral similarity. But then, so once we know angle, this implies LMA equals LKA. Oh, yeah, but we know LMA equals LK. Oh, are you defining L? How are you defining K? Are you defining K to like, are you defining K like this instead? I think that's what you're doing, right? Yeah, as given. Okay, so, and then you're showing angle LMC equals angle LKH. Okay, actually, let me, okay. So yeah, if I hide this circle, we know ALMN is an isosceles trapezoid. So you want to show LMA is LKA. I mean, if we know that, we're done. So I guess, okay, that's the same as showing LMC is equal to LKH. And how do we know? So you said, how do we angle chase?
I drop the perpendicular from O onto BC and then use the similar triangles LMN and LCB.
Okay. All right. So if G is the midpoint of BC, so yeah, LMN is similar to LBC. And then, so I agree with that. LMN is similar to LBC. How does
I separately computed LOE. We write LOE as 180 minus BOE. Yeah, that point, midpoint BC, I call that E.
did you say LOE? I'm sorry.
Yeah, the midpoint of BC, I named it E in my calculations.
Ah, okay. So LOE is 180
yeah.
minus
180 minus BOE minus BOL.
Okay. Or do you mean 360 minus that?
Yeah, 360 minus that.
Okay. And then angle BOL.
Yeah, I write BOL as twice LCB.
Ah, okay.
And LCB is LMN.
Okay. All right, let me think about that just for a second.
Yeah, the same thing I did with the angle LMC, and both turned out to be equal.
Okay, so LKD is LOG, and that's 180 minus, or 360 minus BOG minus BOL.
Yeah.
And that's 360 minus angle A, and
Yeah. Minus twice angle LCB.
Okay. All right. So I'm gonna write this down. So okay. So first, so since ANHM is a parallelogram, that's obvious from the problem statement, and so that means that ANML is an isosceles trapezoid. Okay. Which is cyclic. And then by a spiral similarity at L, we have, or by a spiral similarity at A, triangle LNM is similar to triangle LBC. All right. And so now we can do the angle chase that you mentioned. So we have angle LKD equals angle LOG, which is 360 minus angle BOG minus angle BOL, which is 360 minus angle A minus twice angle BCL, which is 360 minus angle A minus angle NML. Yeah, there will be some config issues. Yeah, I'm just doing it for one configuration. And then, so NML and ANM are the same, obviously. So LKD, then we have angle LMC. LMC is just one.
I wrote LMC equals 360 minus HMC minus HML.
Okay. So, yeah, these two, yeah, it's not. All right. So yeah, I'm going to do that. So we have angle LMC is 360 minus angle LMN minus
It should be LMH.
LMH.
Yeah, and then I replace that with twice LMN.
Minus angle HMC.
Yeah.
Which is 360 minus twice angle LMN. This should be HMC.
Yeah, HMC. And we know that HMC equals angle A by parallel condition.
Okay. And then, okay, so.
Yeah, so both of them are equal, and separating from 180 we get LMKA cyclic.
Let's see. So where did I lose the 2? Oh, this should be 2. So if LM's, so then we have so angle AML is 180 minus angle LMC, which is 180 minus angle LMD. Or wait, LKD. which is angle LKA. So that means that KLMN is cyclic. I'll write it like this. So K lies on the circle ALMN. All right. So thanks for that. So yeah, I'm kind of glad that we avoided harmonic quadrilaterals just because I don't like using, I mean, I love projective geometry, but if the problem doesn't need it, I prefer. Config issues means that basically, so yeah, I'm trying to think how to say this, but it turns out that like L lies on arc AC, but it could have been that L lies on arc AB. Well, actually the problem gives you that AB is greater than AC. So maybe there is no issue assuming like basically if L lied on arc AB instead of arc AC, then maybe we wouldn't have 360 minus all this stuff. But I think we might actually be okay. Yeah. All right, so here's the second problem, which looks probably easier. So in triangle ABC, again, we have AB is less than AC. O is the circumcenter. Let's see how quick we can do this one. Let's see. Trying to drag this down. All right. M is the midpoint of BC. And this idea actually looks a little familiar, like the circle AOM. So we draw the circle through AO and M, and it intersects the line AB again at D and AC at E. So let's see if I can, yeah, I'm going to want to draw a triangle kind of like that. So let me make this easier myself. Okay, so it intersects AB at D and AC at E. That's nice. I didn't have to rename the points. And we want to show DM equals EC. That's kind of interesting. Let me just check that before we begin. So DM is 5.4 and EC is 5.4. And it looks like it's probably just power of a point or something, I would guess. So see ya, Hakan. See ya, Arabian Math. Thanks for participating on the, at least on the first problem. Yeah, Dubai, directive angles to resolve sort of issues like that. Oh, you said it to Arabian Math. All right. Okay. Do we have any congruent, either power of a point or congruent triangles, it feels like, right? So it's got to be one of the two. So so EC, we want to show it's equal to DM. Trig bash. No trig bashes on this channel. All right, so please. No. I haven't done a trig bash yet, so I don't want to do my first one here. Let's see. So where are our congruent triangles? Is triangle DBM congruent to EMC? I bet that's true. Is DBM
that's true.
It is true. All right. And that yes. So that's probably trivial and that probably solves the problem, but let me think about it just because I'm not super smart, so it takes me a while to figure these things out. So okay, so BM is equal to MC. And then, is it obvious angle, let's see. BM is equal to MC. And maybe it's like angle side angle. So I'm just trying to think how to do the angle chase. So angle DBM, it's 180 minus ABC. And is it obvious that 180 minus ABC, is it obvious that angle ABC is equal to angle EMB? Let's see, I have to use, so yeah, it's probably, so, I mean, we have a lot of isosceles triangles, right? So angle, let's see, this is isosceles, right? So angle B, oh wait, I keep getting confused. Wait. Is it obvious that angle ABC is angle EMB? Are you sure those are congruent? Wait, I thought I just saw they were, but this angle 30.2, 30.2, yeah, they're congruent. Yeah, I have to use that it passes through O. And maybe extending MD to AC. Yeah, maybe, I wonder if, let's see, is F, I mean, I feel like this is a nice, no. I feel like I shouldn't even have to do that, but I will try it. I just want to show that DMB is congruent to EMC, right? That can't be that hard. So is ABM equal to EMB?
Extending BM solves it, I think. BM to the other circle.
The other circle, okay. So like this?
HA is tangent to ABC.
Okay.
Because OMH is perpendicular, 90 degree.
Okay, since OMH is 90, that means OAH is 90, which means HA is tangent.
Then angle chasing is
Angle.
CH equals HAB equals HMD. Finishes.
Okay, so all right, so that means that this angle, angle DMH is DAH. Okay, so we got one angle equal. So I'm going to write this up.
Actually, two angle equals we have.
We end up getting two of them are equal. Okay, so let me write that up. So obviously BM is equal to MC, and then let BC meet AOM at H. And then we have angle HAN is 180 minus angle OMH. So angle HAO is equal to 180 minus angle HMO is equal to 90. That means that HA is tangent to the circle. Okay. All right. Whoops, what happened there? That. Maybe this will fix it, I don't know. Yeah, that fixed it. Okay. And that means that angle HMD is equal to angle HAD is equal to angle BCE or BCA. We'll just write that. And then the other angle is also equal because, yeah, we have angle MDA is equal to angle MHA, which is equal to angle MEC. And so by angle side angle, those triangles are congruent. So triangle EMC is congruent to triangle DBM. And so therefore DM is equal to EC. All right. Thank you very much for that solution. And let's move on to the next one. All right. So this problem has X centers. So oh no, actually this one I think is just N centers. So we have a triangle ABC. D is a point on BC. I1 is the incenter of ABD. We draw the incenters of ABD and ACD. And then I1, center of 1, and I2 is the center of the other. O1 and O2 are the circumcenters of AID and okay, that's kind of interesting. I don't think I've seen a problem like this before where it has like the circumcenter of A I1D and A I2D. So O1 is the center of E. And O2 is the center of K. Okay. Whoops. And I01 intersects I. Okay. So I01 intersects I2O2 at P. This is really random. And we want to show P. No, that doesn't look right. So somewhere I did something wrong. Sorry. I1 and I2 are the incenters of ABD and ACD. O1 is the circumcenter of AID. O2 is the circumcenter of AI2D. Oh, okay. I drew these segments wrong. So we need to see where the I1O2 intersects I2O1, and we call that P. And we want to show PD is perpendicular to BC. All right. So, all right. Let's see. Is that very random? This is a very weird configuration. Obviously, angle I1 DI2 is 90 degrees. Maybe that'll help because these are both angle bisectors. So this is the line connecting the centers of two circles, so it's perpendicular to their radical axis. I don't know if that helps. Complete the diameter, maybe. Let me draw. So I'm not. When you say complete the diameter, what circle are you? Extend I1D and I2D to meet the circles. All right. Oh, okay. So it's like, yeah. So since that's a right angle, that means I1F and I2E are diameters. I like that idea. So we could draw this and this. Whoops. What's going on? Okay. Okay, that's interesting. Wait. All right. All right.
REF are on ABC.
Did you say EF? What about
Yes.
EF?
Circumcircle of ABC.
Okay. All right. Let me do it this. Okay. So I'll draw the circumcircle of ABC, and E does not lie. Whoops. And you want to see where EF meets that circle?
No, actually, I asked, are them on the circle, but they're not.
Oh, do you want me to erase it? I'm sorry.
Yeah,
Okay.
it's useless.
And then, let's see. I doubt this is true, but if does DE, yeah, DE doesn't equal DF. Oops. So maybe we could show, like sometimes I like to show something as an orthocenter to show that PD is perpendicular to BC. So let's see, maybe I could let PI to, I could, like, what if I do this? So I'm just gonna, don't know if this will work, but I'm just gonna see where it goes for a second. Yeah, I'm not really sure if that does much. Okay, I'm gonna delete those. So we know, yeah, we want to use that this is the right angle here. And so we know that these are diameters because of that. Is there any other way we can use that fact? So if we can show that di1 squared minus di2 squared is pi1 squared, well, no, that's not what we want to show. What's the best way to prove things are perpendicular? Like we could show, I mean, basically we want to show angle PDF is angle EDA. Is PDF similar to EDA? Let me check. So yeah, these angles I think should automatically be equal, but maybe these angles are also equal. Let's check. 75.8. And 77.8. So close. Let's try this one. Maybe this is. That was kind of close. Let's see. Maybe it's similar to EBD. I don't think so, but I'm just going to check anyways. 54.1. No, it's not 54.1. But maybe there's some other, let's see. Maybe DO1P is similar to DO2E. Well, that would mean that would be isosceles, which I would be surprised. No, I don't think that's right. Are triangles EO2D and DO1F similar? Uh, 14.2. I don't think so. No, 24.6. This should also be 24.6. Okay. I1, I2 is not parallel, right? Yeah, it feels a little like Sawayama's lemma. I don't know how many of you have heard of that. No, but Sawayama's lemma is curvilinear in circles, not. Maybe draw. I don't know how much this will do, but you draw that. So yeah, so this intersection point. Wait, hold on. Was that obvious? Oh wait. Yeah, so these are collinear, I think. I think that's probably easy to prove by an angle chase. So these, but let me make sure that's not just a coincidence, but I don't think it is. I think it's true. And then this right here would be the incenter of triangle ABC. So that, yeah, that must be an angle chase to show that CI2, the angle bisector of this is actually a diameter of that circle. And yeah, that has to be an angle chase because angle DI2E is 90 minus angle DEI2, which is angle DAI2, which is half of angle DAC, and we can show that that is 180 minus. Yeah, that's an angle chase. Okay. All right. So G is the end center of triangle ABC. This looks kind of Desargues, a little bit like Desargues. Or Pappas or something. Doesn't it look like Pappas? Let's see. Is EFCD cyclic? No. Can we use Pappas? But let me draw EF again. We can find one point on this. Let me see if P lies on some circle. PA. No, I don't think so. Let me maybe PE. Just try one more time. PI1, I2. Or maybe P. This looks like it might be cyclic. No. But G is the end center of ABC. That has to mean something. So we have a bunch of harmonic bundles, right? So DB, DI1, DA, DF is harmonic, right? It is an angle chase. Wait, is it trivial? Yeah, I2, O2, and C are collinear by an angle chase. Yeah, I mentioned that earlier. So we have two different harmonic bundles. So BI1, this point, and F are harmonic, and then CI2 and this intersection point and E are harmonic. Does that give us anything? And then we can project it onto the circle. I just don't know if that helps. I feel like there's probably some cyclic quad we're missing. Let's try. Yeah. Okay. So I think we were missing these two cyclic quads. Let's see if we can. It's probably an angle chase, but let's see. So I think EI1GA is cyclic. Yeah, because we know AG is an angle bisector, so we could compute angle AGE. And then can we compute angle AI1E? Yeah, so by an angle chase, we can show this is cyclic, AGI1E, and we can also show AGI2F is cyclic. How would that help? So one way we could show PD is perpendicular to BC. A is the McKell point of I1G, I2D. Yeah, I just realized it's the McKell point, but because, let's see, is that, oh yeah, that's obvious, because A, it's the intersection of E, DI2, that circle, and F, DI1. So yeah, by McKell point, I didn't even need to do an angle chase. Okay, so we have this kind of McKell configuration. And with these angle bisectors, yeah, it is interesting. Feels like, I guess, is P on any circle? I guess not. P is just a different point. It just doesn't lie on any circle, I guess. Unless I'm just missing it. I really wish P lied on a circle. I just don't think it does. Okay. So how do we go about this then? So one way, let's see. P, yeah, there's no way PB equals PC. Although it's really close. But if I move point D, you can see it's not true. Yeah. See ya, Khan. Thanks for joining. So all right. Let's see. How do we show PD is perpendicular? Is angle P, so this is kind of a lucky guess, but is angle, no, that's not 90. So I wonder if we want to draw these points then right here. It's hard to see that other tangency point, but let's see, can I move things around a little bit? Kind of like, I don't, yeah, point P is going away. I want to draw this other point right here. Oops. There we go. So I1H and I2I are we want to show they're parallel to PD. We know they're parallel to each other. Yeah, so this is like, I think we can find a lot of relationships between these lengths, since I1D, I2 is a right triangle, and these are also right triangles. So yeah, I think we want to use that. So I2. So O1A is equal to O1B, and O2A is equal to O2B. So AD is perpendicular to O1, O2. I don't think we've used that fact. But it seems like we should use that fact. O1, O2 is perpendicular to AD. This point disappeared. Sometimes when you move around the figure, tangency points like disappear. So O1, O2 is perpendicular to AD, and we want to show that PD is perpendicular to BC. So one way we could do this is we could try to show we want to show the angle that we want to show angle PDA is the angle that O1, O2 makes with BC. That's one way to do it. What if I try to see where O1, O2 meets BC? This is a complicated figure.
B, O1, O2, C are concyclic.
Oh, sorry, hold on just a sec. This thing won't go away. Why does this thing keep popping up? Don't pop up. All right, I'm gonna have to do this because it keeps popping up. There we go. Drag it back down. Sorry, I know you said something was cyclic, but let me first try this. Oh, I don't think that does anything. Okay, all right. So what did you say was cyclic?
O1, O2, BC.
O1, O2, BC. All right. So we have lots of cyclic quadrilaterals. Oh, no, I don't think so. Let me see. But yeah, O1, O2, BC is not necessarily cyclic. Hold on just a sec, guys. Sorry, I'll be right back again. All right. Thanks for waiting. So
Is DO1 equal to DO2?
Let's see. I don't think so, but no. So we have this Mikkel configuration. So this kind of, so maybe this is like a property of, I was going to say a property of the Mikkel configuration, but So what if we draw the centers of EIG and FI2G, the centers of those circles? So and that's obviously perpendicular to AG. Yeah, we just have to involve P some way, some other way in the we could try to show that PJ squared minus JB squared is PI squared minus IB squared. Yeah, we know this is a right angle. I feel like there's probably even another circle we're missing, I bet. That looks like it passes through O2, but I don't think that's a coincidence. Yeah. Does this circle pass through the midpoint of AD? Let's see. I don't think so, but it's worth a check. Is there anything that... So yeah, maybe we should draw the inner circle of ABC. Maybe there's some kind of homothency. Let's see. So because we haven't really used much that G is the in center. So it's a very crowded figure, but I wonder if there's some kind of homothency, for example, like if we let So it's like if we know everything about this trapezoid, and we know like these angles PI1I2 and PI2I1, maybe that could help us prove it somehow. Let's see. I feel like it would make things so much easier if P just lied on some kind of circle. I'm almost determined to like, you know, is PLI2I cyclic? Or maybe that's just a coincidence. That would be really nice if that were true. No, it's not true.
Isn't I1, I2, Fe complete quadrilateral, and I think we can find a ghost line here.
A Gauss line? Okay.
Yeah, ghost line of complete quadrilateral.
Okay, so I1, I2, EF, is that kind of what you were thinking?
Yeah.
Okay, so because O2 is the midpoint of I2E and O1 is the midpoint of I1F. And then, yeah, so we kind of see where EF meets I1, I2, maybe. Right, let's think about this. So, no, I kind of see what you're saying. We have two midpoints. But yeah, I guess that would be kind of adding a lot to the figure, but I'll just do it just to show it. Basically we're saying like we're saying that O1, O2 passes through the midpoint. If we draw the midpoint of N and B, we're saying O1, O2 passed through that. Yeah, it's kind of adding a lot to the figure though. That's the thing. I'm gonna hide it just for now. Yeah, I'm gonna erase it. Just maybe there's like, I don't know. Maybe there could be something different that helps. Like a different Gauss line or something. Let's see. All right, I'll spend 10 more minutes on this problem, and then if we don't get anywhere, we can move on. Let's see, PD perpendicular to BC. So I guess another way to say that is, let's think. we want to show that pi squared minus pi1 squared minus or no, let me think actually. Is there any way I can translate that? I wonder if P lies on the radical axis of I1 and I2. Let's see, I could check that this way. See if it has the same, the tangents have the same length. This is hard to check. How do I do this? Sorry. I'm checking if P lies on the radical axis of these two circles. So I want to see, does Pn equal Po? That's so hard to check. Sorry. Does that help? This is, let me see. I really want to see if P lies on the radical axis of those circles. It's just hard to draw it. I don't think so. No, it's not true. Okay. The line through the orthocenter. We did some radical axis. What orthocenter? G is not an orthocenter. Oops, sorry. So let's go back to, so we want to show PDF is equal to EDB, right? Maybe we could use the isogonal line limit here, the Gauss line. Oh, so I forgot the lemma, but like the four orthocenters, what are the four orthocenters that are collinear? I know there's that lemma, I forgot what it is. But I've seen it before. So yeah, let me try dropping perpendiculars from P. So yeah, what are the triangles that I should have the orthocenters of? Just because I don't remember that lemma.
I think we can just move on to the next one for now.
Okay. All right, I'm going to move on to the next problem, but this seems like a good one. All right. this problem seems tricky. It's really short. See how short the problem is? But I think it's harder than it looks. So let's see.